Okay, so far we've covered a lot of auditory attentional processes, but what about vision? So what about how, when we've got a visual scene in front of us, how can we selectively move our attention? And again, we're not talking about moving our eye gaze around the visual scene. It's more, how do we move our attentional resources around that visual scene to process different elements? And there's been a number of metaphors proposed to explain how this might occur. One of these is the idea that it might operate like a spotlight. So as you're focusing on the scene, maybe I could flexibly move my attention around in a sort of fixed diameter, but moves across the visual scene like this. Alternative metaphor is that it works like a zoom lens. So depending on the task, maybe at sometimes we want to process everything broadly, or at other times we might narrow down that focus to process a particular object. Okay, so the first of the metaphors is this spotlight metaphor. And this was originally built on the work of William James, who described attention as very much resembling a spotlight that has a kind of focus, a margin, and a fringe area. And essentially, Michael Posner was the sort of one of the main proponents of this spotlight metaphor, who argued that shifting attention requires moving this spotlight around, and then our attention illuminates a portion of the visual field, and everything that is inside that attentional spotlight is processed at a high level, high resolution. It's actively processed, whereas everything that is outside, it decays rapidly and is processed at a very low level resolution. So if you remember at the start, we considered some of the personal insights of Helmholtz, who did the sort of ingenious but somewhat crude experimental studies on himself, where he would test how his visual attention could roam around that array of letters. We can also see examples of how our attentional spotlight can zip away and move around in contrast to where our eye direction is. So again, in those original studies by Helmholtz, he was holding his eye gaze, his visual fixation was towards the center of the array, but he was just flexibly moving his visual attention around the scene. So one example of how this attention flicks around from the sort of left and the right of the screen is demonstrated by something known as the Posner queuing task. So in this task, participants are asked to press a button as quickly as possible when they see a target appear. And this target can appear either on the left or the right hand side of the screen. Participants are told to maintain their focus on the fixation cross. So if you look at the screen right now, you've got to maintain your fixation or eye gaze directly towards this. Now, in some trials, participants are given a little hint about where the target was going to appear. So if you watch the screen very closely, you're going to see a flash of light in the box on the left-hand side of the screen, and the target will then appear on the left-hand side. So again, keep your visual fixation. So keep looking at the central fixation cross. So we know that you can keep your visual fixation at the center, but our attention might be directed a little bit to the left-hand side. So that's an example of what was known as a kind of valid or congruent compatible trial. So again, your job here is just to respond, indicate which side is the target going to appear. Alternatively, on a small proportion of trials, the cue of light might appear in the opposite location to where the target appears. So let's see an example here. So that little cue is appearing on the left hand side, the target is appearing on the right hand side. And again, in the experimental setup, these little hints or cues are provided just a fraction of a second before the flash of light. And in this case, I've illustrated it with a star, before this flash of light appears on the left hand or right hand side. And participants, they're not having time to make a saccade, so to make an eye movement to the left or right hand side of the screen. And they check this by looking at their fixation of their eye. And the researchers were basically interested in studying what was the influence of those little cues. So did they draw your attention to the left or the right hand side of the screen? And if that's the case, it would then mean that you should be faster to respond when that cue is drawing you over to the appropriate side, so it's drawing your attention to the left or the right, and the target is actually going to appear there. And what they found is that people are about 50 milliseconds faster to respond and detect light when they've been given a clue as opposed to when they haven't been a clue. And this is a pretty strong and significant advantage that's in there. So again, the visual fixation is not changing, they're looking straight forward, but the fact that they're faster suggests that there's something other than the eyes, which don't have time to shift, has moved to the area where the light was expected, and that's speeding up their response time. So from experiments like this, Posner and others argued that it's our attention that's moving around the visual field, independent of our eye gaze direction. So again, if you look at the data that's plotted on here, you get a small difference in reaction time on targets that were presented to the left or the right of fixation. You don't need to worry about that. But what's kind of critical in here is that when the cues are valid, your response time is much quicker than when they were invalid, which is suggesting that that little cue has drawn your attention to either the correct location, or it's distracted you by drawing your attention to the inappropriate location. But it's also the case, others have likened attention to a zoom lens on a camera. And essentially this model or metaphor inherits all of the properties of the spotlight model, but it's just added the property of having some flexibility in changing the size of the attentional spotlight. And this size change mechanism is inspired by the sort of zoom lens one might find on a digital analog camera. So the zoom lens of attention can be described in terms of having this inverse trade-off between the size of focus and the efficiency of processing. So again, if we think we've got this fixed attentional resources, we can be flexible in the way that we use these resources. We can either spread them thin but widely over a large degree of focus, or a large region, or we can narrowly focus these attentional resources on one specific area and focus in much more detail. So one example where you might think of this is that if you're, say you imagine driving your car down the road, and under normal conditions we have a relatively large and wide focus, so we're needing to pay attention to the entire visual field in order to anticipate possible dangers that are occurring up front, and we process everything at relatively low level resolution. But say if we then encounter a hazard that's coming up on the road, it would make sense to flexibly narrow down our visual attention and focus on that specific hazard that's in front of us in a bit more detail and process that. So again, we have either this narrow focus where we process what's in there at a much higher resolution, or a wider focus. Now, in a study that provides a nice test or illustration of the zoom lens theory, LeBurge presented participants with a series of 5-letter words. So examples might be house, train, carpet. I know carpet has 6 letters, but all of these were 5-letter words. And they asked participants to perform 2 different types of tasks. In one condition, they had to do a very straightforward categorization task. So you had to say, what category does this word belong to? And in the second task, they had to respond simply to the middle letter of the word. So in the case of train, you would have to indicate that yes, the middle letter was A. So in both conditions, a pretty simple, straightforward task. Now the trick in here is that sometimes they would insert a probe, and I don't mean this in a kind of alien way, but to examine how participants were directing their attention, on some trials a probe digit would appear in one of the 5-letter positions. So for example, if they saw the number 7, they would have to respond to it. And that number 7 could appear anywhere within this letter. And you think in these two different conditions, we have different ways that you might want to flexibly direct your attentional resources. So in condition 1, our performance is probably going to be best if we use a relatively wide lens that allows us to process the whole word. So in the case of house, our attention will be focused on the entire word because we want to categorize it. Whereas in condition 2, the only thing that really matters for us is that middle letter. So it might be the case that we really narrow down our attentional focus and just dedicate it towards the central letter there. So to test this, they then looked at what was the reaction time of participants to detect and notice the probe digit depending on its location within the word. So what we've got plotted here is the mean reaction time on the y-axis, the probe position on the x-axis. So 1, 2, 3, 4, 5 correspond to which letter order was it? Was it the first letter in the word, the second, the third, the fourth, the fifth? So obviously the third letter is the middle letter here. In the dashed line, we see a pretty equivalent reaction time for that probe digit, irrespective of where it was appearing. So whether it was presented as the first, the last, or the middle letter doesn't make a difference to the reaction time. The thing that's interesting is in the continuous blue line is that participants were much faster responding when it appeared in that middle location, so where they might have narrowed down their attention that they were focusing, whereas they were much slower to respond when it appeared outside of that, so when it appeared as the first or the fifth letter. So again, it should be within your visual field, but it's supporting this idea that clearly when the task demands that you focus on a much narrower region, it's only then that we're detecting the probe when it appears in that location, whereas we are a little bit slower when it appears outside of this region. Like many metaphors, it's probably wise not to take the attentional spotlight or the zoom lens too literally, and there's subsequent findings that kind of question whether this zoom lens metaphor is applicable. So one study by Orr and Pashler that kind of questioned whether this zoom lens always applied. So they took a nice methodology where there was a high probability that the target that you need to respond to would appear in either of these blue locations. So you've got one on the left and the right hand side. So again, on the majority of trials they're appearing in these two spots. So that would make sense. It would be efficient that you would direct your location towards these two regions. Now if we were taking a zoom lens approach, theoretically this would be probably the most likely explanation for how you would then direct that attention. So you would cover the left and the right regions with the sort of wide zoom, and then that also by default kind of cover the central region. Now what they would then do is on a small proportion of trials, they would also put in a target that would appear in what's labelled as the near and the far location. So that near one is right in between where most of the other targets are appearing. And if we're using this zoom lens approach, you should detect that most of the time. That's right in the middle of our sort of zoom lens. Whereas you probably wouldn't expect good performance in the far location. But what they found was that participants were really good at detecting the targets when they appeared in the expected left and the right boxes, but when it appeared in the middle in this near location, the accuracy of target detection dropped off dramatically. We actually end up possessing multiple different spotlights that we can direct around the visual field. Either way, it seems pretty convincing evidence that the zoom lens isn't applying in this particular case.